Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Ed Young with us today. Hello, Ed.
Hi, thanks very much for having me here.
Well, thanks for agreeing to talk about your very awesome article, which we're going to get to shortly. And Ed, what is your geolocation? Where are you at?
I'm in Los Angeles at UCLA. Yeah.
Oh, how's the rain?
Pause for a moment. It's
Oh,
sunny.
it did.
Yes, 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 yes.
So I'm in Phoenix on this November 18th of 2025 as we record this, and we're getting the same storm system. So it actually
Ah, okay.
rained this morning on us. So yeah, it's quite the atmospheric river, I think is what they're calling it. So
Sandbags all over campus. Yes.
oh, okay, we're not that bad. I also live on a little bit of a hill, so I'm a little bit protected from that kind of stuff. But yeah, very cool. Very good. Oh, I'll just be curious. Ed, how long have you been at UCLA?
I've been at UCLA for 24 years.
Very awesome. Cool.
Yeah.
Very nice. And Ed, in those 24 years, and maybe a little bit before that, what do you like to do for research?
Well, that's a really interesting question for me. I'm pretty eclectic. I'm an isotope geochemist by training.
Okay.
I've
Mhm.
spent most of my career studying stable isotopes from carbon, oxygen into magnesium, iron, silicon, and using these isotopes. When you're an isotope geochemist, you get involved in all kinds of research, from terrestrial to extraterrestrial.
Yep.
A lot of my research has been devoted to using meteorites to understand the origin of the solar system and
Uh-huh.
particularly isotopes.
Very cool.
Then more recently, I've moved into all of this paper exoplanet research,
Very
partly because of the influence of my colleagues who are.
Yeah. Speaking of colleagues, so I'm at ASU in the School of Earth and Space Exploration. We have quite a few isotope geochemists
Yes, you do.
I
Yes.
hobnob with. So we're all in good.
Yes.
And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
Yeah.
Differentiation, the exception, not the rule. Evidence for full miscibility in sub-Neptune interiors. And Ed, take us away.
Okay. So I guess the first thing I would say about this is it's a really interesting collaboration. Um, my co-authors include Aaron Werlin, who's a graduate student now at Munich, who came to us to visit from ETH. And the project really started with Aaron standing at my whiteboard and saying, "Why can't we do this?" And I said, "Yeah,
Okay.
we can do this." Okay. And then Sarah Markham is my graduate student who's heavily involved in the ab initio calculations, molecular dynamics calculations.
Uh-huh.
And she's learned her trade from Lars Stickrud, who's my colleague here at UCLA.
Very nice.
And then Kees Duleman, this is really interesting. Kees is a card-carrying astrophysicist.
Yes.
But we were at a meeting and I was presenting some of this, and he said, "Ooh, ooh, ooh, I can do this better." And it turns out he can. He's been developing a convex hull method for doing free energy minimization.
Oh, nice.
And so we applied his method to actually do the working diagrams in this paper. So that's been really fun. He's immersed himself in the minutia of geochemistry. It's really fun to watch.
Very cool. Nice, nice interdisciplinary there and great shout out.
Yeah.
Okay,
So
let's
yeah.
get to it.
Well, so I would describe this as kind of a 20th century answer to 21st century problems, and that is that we're using the tenets of um, phase equilibria or equilibrium chemical thermodynamics to understand the nature of sub-Neptunes. In the introduction of the paper, I make the analogy with what we knew about the sun in the 1920s. And to some degree, there's a parallel because we look at bulk densities of sub-Neptunes and we get wisps of little molecules that are in their atmospheres,
Yes.
but we have a really hard time understanding their fundamental nature.
Right.
And so we attempted to do this using what we've learned about phase equilibria of these exotic systems. And so the key ingredient is hydrogen. We need to have a better understanding of where hydrogen lives at the extreme conditions
Yes.
that apply to sub-Neptunes.
Cool.
So this was an effort to do that. We're building on, as I say, ab initio molecular dynamics calculations,
Uh-huh.
which tell us where hydrogen should live. And then we try to apply that. But the problem is this is in its infancy. The calculations and the data are sparse.
Okay.
So this was an attempt to interpolate and extrapolate into a more full chemical system. So let's see.
I'm with
I
you.
could start by going to, let's see, do I want to go to let's go to figure one right away.
Okay, we will do some iron-rich metal cores and differentiation in figure one, Gibbs free energy. There we go.
Right. So this gets right into the heart of it. And this is that if no one's ever thought about plotting free energy against mole fraction, this is what the plots look like
Cool.
in the so-called binary system where you have
Hmm,
mixing of silicate on the left of the diagram with hydrogen on the right of the diagram. And this
hmm.
is what the free energy looks like. And what you see is a little dimple, sort of where that red dot is. There's a little dimple in the free energy surface.
Okay.
That little dimple tells us that the mixing is non-ideal. In fact, we learned that it's non-ideal by doing calculations.
Uh-huh.
And that is the heart of this paper, is that non-ideality of
Okay.
the mixing.
Okay.
And so what it tells us is that at low temperatures and pressures, we're going to get two separate phases in our system: silicate, which is the black dot on the left,
Yes.
and a hydrogen-rich phase, a supercritical fluid, if you like, which is
Hmm.
the dot on the upper right.
Correct.
And
Yes.
I'm colorblind, so if I get the colors wrong,
It's all perfectly good.
I think that's a blue dot, right? I
It's a
think.
blue dot. Yes, yes. And let's see. Let's ask a question. What is the tie line?
So the tie line connects the two coexisting phases at equilibrium.
Hmm.
And so that tie line is connecting the two equilibrium phases. And you can imagine that that line wiggles around as you change temperature and pressure.
Sure. Okay.
And if we so that's the basic thermodynamics. But if we go to, let me just jump right ahead to
Sure.
figure three, if you'll allow me.
Sure. You're the driver. Let's go to figure three. Some awesome equations in this article, people.
Yeah.
These are the initial final conditions. Here we go.
So in figure three, this is an ab initio calculation. You're seeing atoms. So for example, the big red atoms are oxygen,
Hmm.
little gray ones are hydrogens.
Yes.
And in this calculation, the hydrogen and the silicate made up of silicon, magnesium, and oxygen, you don't really think about it. Rocks are made up 90% by volume oxygen. So they're basically just hot oxygen with all the other atoms stuffed in between.
Good.
So so there's your silicate melt
Yes.
at the bottom and a hydrogen gas at the top.
Uh-huh.
And in the ab initio calculations, we let them run, in this case at 4,000 degrees and 3.5 GPa. This is the
Hmm.
specialty of Lars Stickrud. He's the one who does these calculations so beautifully.
Nice.
And what we see is the system moving from left to right, it completely mixes.
Yes.
It's complete miscibility of hydrogen with silicate.
Hmm.
If you scroll down to figure four,
Yes.
to show you that this is
Yeah.
not inexorable. Um,
Whoops.
oh,
Before, gotta go up. Here we go.
oh yeah, over there. Yeah, sorry. If you look at figure four, that's the same system, but at lower temperature and pressure. And
Okay.
see, in that case, they don't mix.
Uh-huh.
Instead, what you see is evaporation. You see little SiO molecule
Yeah.
and a water molecule. These are the things that end up in the gas phase at high temperature, but it's not miscible.
Okay. Right. You
So,
keep the two phases. Hmm.
yeah. So actually, if you just shift to the left a little bit,
Okay.
uh,
Go to figure two. Here's
yeah,
our phase diagram, isobaric.
when you take those Gibbs free energy surfaces I showed in the first diagram, you can use them to construct a phase diagram like this.
Hmm.
And the phase diagram shows you the regions where you have two phases and when you have one phase, a la those ab initio calculations I just showed you. So,
Yes.
for example, above about 3,600, 3,700 degrees at 4 gigapascal, hydrogen and silicate form one phase.
Yes.
And below those conditions, they form two phases, and the equilibrium compositions are given by that tie line. You see the dash line
There
there.
we go. Hmm.
And they evolve as temperature goes down, for example.
Very cool. Okay.
Now, we have two ways of describing this. One is called the binodal,
Hmm.
which gives us the equilibrium compositions. And then there's the spinodal, which tells us that that's where kinetics cannot prevent us from forming two phases. Inside the spinodal, two phases will spontaneously erupt from one
Yes.
phase.
Second derivative of the Gibbs. Hmm.
Right, right. So that's right.
Huh.
So that's our phase diagram. So now what we did in this paper, this was understood. We've had a couple papers on this,
Hmm.
but we realized that we could go a little further and say, what happens to the iron silicate system?
Hmm.
So what we learned is that the iron silicate system, there was enough calculations that we could do the same thing for the iron silicon system.
Nice.
And that's shown in figure 5.
Okay, let's slide down to figure 5. So we're going to go from binary to, not quite yet. No, not figure 5. Yes, figure 5.
Yeah, figure 5. And there you see MgSiO3, that's our surrogate for silicate. And iron, we start with iron in the top and silicate on the bottom on the left side of the figure.
Okay, I'm with you.
And allow this figure to run in 0.5 femtosecond steps, uh, for what that's worth. And and you see it become one phase as well.
Yes.
And so we were able to estimate from previous work on the MgO Fe system and this one calculation for the MgSiO3 Fe system,
Okay.
a crude, what we call subregular solution model for that binary mixture when it becomes supercritical versus when it's subcritical, or when it has complete miscibility versus immiscibility.
Yes.
And then lastly, there's a lot of experimental information about the iron hydrogen system.
Okay.
Everybody knows that hydrogen is soluble in iron, but how soluble it is depends on temperature and pressure.
Yes.
And there's enough calculations these days to realize that it too becomes completely miscible at extreme conditions.
Okay.
And so in figure 6, we show the iron hydrogen system that we estimated from experiments. And that's another one of these phase diagrams.
Okay, very good. One phase, two phase. There's a solubility limit in green.
Yeah. So that line on the left that you're pointing to is that's sort of a constraint on the left limb of that phase diagram. If you
Mm-hmm. Mm-hmm.
And its closure, we don't know for sure that it closes at exactly 5,800 degrees at this pressure, or whether it's 5,500 or 6,000, but
Fair
it's
enough.
somewhere in that neighborhood.
Yes, fair enough. Okay, I'm with you. Uh-huh.
Okay. So we have these three binary systems.
Mm-hmm.
And if you want to look at equation 4, for example, you can
Let's
scroll
take a
down.
look at figure equation 4. There we go.
Yeah.
Here's
So
our
that's an example of what the binary system free energy looks like. You have a single mole fraction, which relates the two end member compositions.
yes.
So in this case, it's the mole fraction of hydrogen.
Mm-hmm.
And you have interaction parameters, L sub AB, L sub B1.
Mm-hmm.
And then RT is, gas constant times temperature. And
Yep.
that second term is just the entropy of mixing, the ideal entropy of mixing.
Yes.
And the first term is where the non-ideality of bonding in the enthalpy lives.
Cool.
And this is a classic, what they call asymmetric or subregular solution model for Gibbs free energy for a binary system.
Mm-hmm.
So here's what we have. We have three binary systems with their own individual free energies,
Yes.
and we want to mix them in a ternary diagram, a
Cool.
three-component system.
Cool. Okay.
And that can be done. We know how to do this. That's what I meant by a 20th century solution to a 21st century problem. We've known for a long time, going back to Ganguly and before that, how to take three binaries and turn them into a ternary system. And that's shown in equation 6. So the whole paper is basically built on equation 6.
Okay, well, let's take a look at equation 6, and there we go. And it's got the same form, just many more terms.
Right, many more terms. And so we can then construct the free energy surface for a system that's composed of silicate,
Okay.
iron metal, and hydrogen gas. And now that's starting to sound like the ingredients for a sub-Neptune.
There
Right.
you go. This does.
Right.
Okay.
And so most people have modeled sub-Neptunes as being their densities and so forth as being some mixture of hydrogen-rich atmosphere or water, silicate, and usually some kind of iron core. So we wanted to take this ternary system and see whether or not that makes any sense.
Okay. Binary, 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 and finally the mixed term. I'm with you. Mhm.
Okay. And that last mixing term, for those that care, we've set LABC to 0, which is intentional because we don't really know what the ternary mixing term would be,
Okay.
but would be strange if it were to dominate over the other three binary legs. So
Yeah.
that's set
Okay.
to 0.
Okay. Thanks for that caveat. There we go. Here it is. We set it to 0. There we go.
Okay. So,
Mm-hmm.
if we go to figure 7, we're looking at the free energy surface in the ternary system composed of iron metal, pointing right at you there on that apex.
Mm-hmm.
MgSiO3, our surrogate for the silicate that comprises the planet,
Yes.
and H2, which we take to be basically the primary atmosphere of a sub-Neptune.
Okay. Mm-hmm.
And this is at fairly low temperature and pressure, and you're seeing tie lines connecting in this case, if you look at the nearest tie line to us, you're seeing an iron-rich phase connected to a silicate-rich phase,
I'm with you.
so forth. And so those tie lines tell us the
Cool.
phase equilibria, what's in equilibrium with what as a function of temperature and pressure.
Yes, I'm with you. Mm-hmm.
So then the next step is we built some planet models, using the equations of state of MgSiO3,
Okay.
and my student Sarah Markham has figured out that the equation of state, the compressibility of MgSiO3 plus hydrogen, is very similar to MgSiO3.
Okay.
So we can use that equation of state of liquid MgSiO3, and published equations of state for iron metal, for example, and build a model, and published equations of state for hydrogen, I should say, and build models for sub-Neptunes.
Okay.
Look at how their temperature and pressure varies with depth in the sub-Neptune,
Yes.
then calculate at each one of those temperatures and pressures, or a subset of them, what the phase diagram looks like, and predict whether or not they should have metal cores or not.
Yes.
Key point.
Yes.
So let's see, if we go to, I can show you how the diagrams work in figure 8.
Okay, let's take a look at some tertiaries, I believe. Yes.
Right. So these are
Tertiaries.
fun diagrams, and I don't. Some people were schooled on this as undergraduates, and some have never seen them before.
What's a
Challenging.
triangle diagram? Right.
Yeah, right. Okay, so what we're looking at is in this diagram, wherever you see the blue tie lines connecting two dots,
Yes.
that means we have two phases in equilibrium with each other.
Mm-hmm.
And whenever you see one field that's very, very pale gray, that means there's one phase, only one phase,
Yes.
not where you're pointing, but above it.
Mm-hmm.
Up there. Yeah.
Yes. Yeah. One phase region. Uh-huh.
Right. And then started curious. I just showed this diagram because it's fun. Up above there, you see there's two liquids that are immiscible, two liquid phases together, which is
Yeah.
so. In any event, to
Oh,
get oriented on this diagram, you can look
okay.
down at the bottom. We've labeled the bulk composition of Earth.
Mm-hmm. Right
Actually,
here.
that's the bulk composition that my colleagues and I, in another paper earlier last year, we applied these same principles to actually forming Earth and how Earth got its water.
Okay.
And this is just showing you that here you would see Earth would have an iron-rich phase in equilibrium with a silicate phase. That would be its core and its mantle.
Yes.
But when you get up to the higher hydrogen abundances, like a sub-Neptune, and that's my little symbol for a sub-Neptune in the middle there. By
Mm-hmm.
the way, we need a symbol for
Yeah, I was
sub-Neptune.
going to say I've never seen that one before, but I like it. I
Well,
like it.
it's Neptune with a circle. I don't know what to use, but anyway, so the sub-Neptunes are squarely in this diagram in the one phase field.
Yes.
And then Neptune up above is also
One
at the
phase.
very top is in the one phase field.
Yes.
Okay.
Uh-huh.
So that's the way you read the diagram. Tie lines give you two phases that are in equilibrium. With no tie lines, you're in one phase.
Yes.
And that is at one, we call that an isothermal isobaric projection because that's at one temperature and pressure. This diagram
Yes.
applies to one temperature
Here,
and pressure. Right.
5,300 K and about 13
Right.
giga-PA. Mm-hmm.
So if you just slide over to the right, here's a pressure versus radial distance in the
Ooh.
core of the sub-Neptune. And I mean core in an astrophysical sense, meaning everything that's not the envelope.
Yes.
Um, and that's plotted against radial position, where one is the core envelope interface right
Okay.
there. One.
Okay.
So I've labeled A, B, C, D, E, and F here as being positions that we're going to monitor using our new phase diagram as we go through this planet.
Okay.
And there's a little bit of iteration that goes on because we're going to find out whether it's two phases or one phase, and then we have to recalculate the model so it works like that.
Well, good. It's a little bit of self-consistency there as we go through. Mm-hmm.
Yeah. So I just wanted you to see where those panels are. And the main thing to keep in mind as we go to the next figures is that even when we're at position D here, A, B, C, D, we're
Mhm.
still only 5% into the depth of the planet,
Right.
right?
About 0.95.
And
Yep.
that's at about 20 gigapascal. Okay.
Mhm.
So we can go to
Okay.
figure,
Okay.
next figure, figure 10.
Good.
And this
Mm.
is the money slide, I would say.
Ooh, nice.
So,
Let's see if we can blow that up a little bit. There we go.
okay. So you're
Okay.
looking at a sequence of phase diagrams from basically at the surface in panel A with
Mm.
increasing pressure and therefore depth into the sub-Neptune,
Okay.
A, B, C, D, E, and F. So let's start with A. You see the little sub-Neptune symbol there,
Yes.
and that's the bulk composition of the sub-Neptune. And what you see is that there are actually three phases in equilibrium at the surface of the sub-Neptune. On the left is the silicate.
Ah,
It has a fair amount of hydrogen in it. This I should explain is not in mass fraction but mole
full
fraction.
fraction. Yeah.
So that actually that symbol for the sub-Neptune represents 2 weight% hydrogen.
Okay.
For those that are keeping track.
Mm-hmm.
So you see a silicate that has a fair amount of hydrogen in it, in equilibrium with an iron-rich phase on the right. That's over there, and then they're both in equilibrium with a gas hydrogen-rich phase on the
Wow.
top. So it's a
Okay.
three-phase triangle, right?
Mm-hmm.
So that's basically right above the interface between the envelope, the gaseous envelope, or the supercritical envelope.
Right. These letters correspond to these things. Yeah.
Yes,
Yeah.
panel A,
There we
right?
go. Okay.
Yeah,
Just remind myself and people. Okay.
that's
Very
great.
good.
So now we go to panel B and we dove into the core. Okay.
Mm-hmm.
So now we have only two phases in equilibrium. We have a hydrogen-rich silicate and a hydrogen-rich iron metal. Those are the tie lines that go right through. The way you read this is the tie line that goes right through the bulk composition is the one that applies.
Okay. Mm-hmm.
That's mass balance. It's called the lever rule.
Cool.
So
Okay. Oh yeah. Okay. Mm-hmm.
So there we are. So we have those phases. Now, as we increase from 4 GPa to 8.6 GPa, and the temperature rises commensurately,
Yes.
you still have the two phases, but they're beginning to mix. You see how the tie lines are connecting phases that are getting closer and closer together in composition.
Yes. Uh-huh.
Yep. And Earth, by the way, down
Technology
there
is
is doing
changing too.
something very different. Earth has a iron-rich core and a silicate mantle, and it's not changing very much because it doesn't have that much hydrogen to affect its phase equilibrium.
Right. Very cool. Okay.
Okay, go to D.
Ology is morphing. Okay. And whoa, okay.
Right. So now it gets kind of
Something
cool.
happens.
Yeah. So this is the title of the paper. At 20
Hmm.
GPa, the sub-Neptunes with that much hydrogen are one liquid phase or one supercritical phase. I should call it a supercritical fluid really because it's a mixture of hydrogen, silicate, and iron.
Hmm.
So that is a supercritical magma ocean
Cool.
that we would predict would comprise the core of the sub-Neptune. And there's no metal core. There's no central high density core. It's just one phase.
What happened to differentiation? Yes.
Right. Earth, thankfully, retains its core.
Still
Its
there.
phase diagram is doing the right thing, more or less.
Cool.
Then, as temperature and pressure both increase as you dive deeper through the core of the
Uh-huh.
Neptune, the two-phase field grows, but it never grows to completely overtake the sub-Neptune. Now,
Right.
we've refined these calculations. We can basically say that when the core has less than about 1% hydrogen, so the core would actually lie a bit lower than the bulk there.
Okay.
So move your cursor down. Yeah, right about there. The
Right
core
about
would be
there.
there.
Hmm.
When it's at about 1%, it's still one phase. And even a little bit lower, it's still basically one phase because you're sitting on that dot there. And so that
Yeah.
would still basically be one phase. But
Yes.
when you get well below 1 weight% hydrogen, then you erupt into two phases again.
Boom. Right. Right.
So
Across
to the
the.
extent that sub-Neptunes have uh, 1, 2, 3, 4, 5 weight% hydrogen, these phase diagrams predict that they would not have metal cores.
Yes. Correct.
Yeah. And then
I'm with you. I'm
all
with
the
you.
way at the center of the planet is the one on the right. So it's basically
Yes.
the same idea.
Hmm.
So that's really the important point here is that and what's interesting is it's a melding of when I said 20th century, I mean ternary phase diagrams have been around forever, right? And people use them all the time because they're a nice visualization.
Yes.
But we're applying it to a system where the phase equilibria is not that well known, which is hydrogen-rich systems at extreme conditions.
Yes. Okay.
And the ab initio molecular dynamics calculations are essential to making progress to understanding what's the nature of a sub-Neptune.
Good, good. Nice mixture of stuff.
Yeah.
TFTs, equilibrium thermodynamics,
Yeah. And
two
so then
models.
the next figure, you might be inclined to say, well, that's all well and good, but how robust is this?
Fair enough.
And that's fair
Sensitivity.
enough. So
Mm-hmm.
probably we made the argument here that probably the least well-known interaction parameter is the AC parameter between MgSiO3 and iron. And here I've
Okay.
shown what the phase diagram looks at 5,318 degrees K at 20.5 GPa. Those numbers happen to be along the isentrope in the planet. So that's why
Okay.
they're specific numbers.
Okay. Mm-hmm.
So that's what it looks like when that interaction parameter is 80% of the value we used. And
Okay.
right is when it's the value we used, and on the far
Yep.
right is when
Yep.
it's
We saw that.
20% higher.
Uh-huh.
So that gives you
Okay.
some sense of how well constrained or poorly constrained the calculations are. We find basically 10, 20% variations in these interaction parameters don't change the results very much.
Mm-hmm. Mm-hmm.
So
Interesting little island over here in 1.2.
yeah,
Yes.
that's neat. But it's still, you still be, I mean, even if you were right in the middle of that field, the compositions of those phases would be so close to one another
Yeah.
that I'm not sure you could count that as differentiation. But it's interesting thing. There's more to be learned for sure in this.
Definitely. Very
Yeah.
cool. Very cool. We'll come back
So
to that point. Mm-hmm.
yeah, and so then what we decided to do is, okay, if there aren't cores, can we somehow identify that in the for example, the bulk densities or mass radius relationships in these planets? Of course, mass radius relationships with sub-Neptunes are notoriously degenerate.
Yes.
Um, there's that intermediate region where they're not quite underdense enough to require a primary atmosphere. They're just about right if you want to have 40% by mass water, so you have the Haitian world arguments and so forth.
Yes. Yes.
And so the question is, how does all this feed into that? So the first thing we did to address that is in Figure 12.
Okay. Yeah, we're gonna do some. Ooh, beautiful. Mm-hmm.
Yeah. So Figure 12 compares. Um, on the left is what I would call a classical model,
Okay.
where we have a hydrogen-rich atmosphere, but in order to try to, um, well, a hydrogen-rich atmosphere, and then a silicate magma ocean mantle,
Yes.
and an iron core. And I should say, and I haven't said anywhere else, but I should point out that when you have these big, deep primary atmospheres, they have such great optical depth that they can maintain a magma ocean for 1 billion years.
Yes.
So someone might ask, why do you keep modeling these things as magma oceans? And it's because we're interested in the primary atmosphere planets, and they have the capacity to insulate the
Yes.
system to prevent it from cooling such that it goes below the solidus. So,
Yes. Okay.
okay. So we have this silicate magma ocean, a metal core, pure
Yes.
metal core, and a pure hydrogen atmosphere. And
Uh-huh.
that's sort of a classic model. And this is for a 6 Earth mass planet with 2 weight% hydrogen.
Yes.
And you'd say, where does the hydrogen live? The hydrogen lives in the atmosphere, but we also put in
Mm-hmm.
1.3% hydrogen in the silicate mantle to match the amount that we're going to get in the model on the right. It
Uh-huh.
is an attempt to compare like with like.
Yes. Yes. Okay. Okay. I'm with you. And so here we got on the right.
So on the right is the miscible planet based on these phase diagrams that I showed you. There's
Yes.
no metal core.
Right.
It's still 2% hydrogen. It's 6 Earth masses, but it's considerably smaller. It has a radius of 2.9 Earth radii rather
Mm-hmm.
than 3.5.
Mm-hmm.
Um, and,
Mm-hmm.
and it has an envelope that has a higher weight fraction. Part of that's because there's a fair amount of silicate actually in the gas. That's what the phase diagram requires. This is a higher molecular weight gas at the base of the atmosphere.
Yes. Yes. Uh-huh.
So that's sort of showing you that we tend to think if you have 2 weight% hydrogen, it's completely degenerate as to where it is, and you wouldn't know the difference. But here, there is a difference. There's a difference between where the hydrogen lives and how it's distributed in the planet with respect to its bulk density.
Very nice.
And even though it's interesting though, planet on the left is swelled up, even though it has this dense iron core, and that's because that's a little bit of ancillary effect because that in the classic model here, the atmosphere is pure hydrogen. So it's
Hmm.
puffed way up. So really, we need to do a comparison where we don't have a pure hydrogen atmosphere because that's masking the effect of the metal core.
There you go.
So in figure 13,
Yep. Yes,
we do
yes, yes.
just that.
You do just that. There we
Yeah.
go. Uh-huh.
In this case, everything is identical in the two planets, with the exception that the planet on the left has a pure iron core.
Okay.
Planet
Okay.
on the right does not.
Right.
So the planet on the left has a transit radius of 2.6 Earth radii, and the planet on the right, as I said, is 2.9. And so it makes some difference as to what the mass release relationship is when you don't have the metal core.
Yes.
Um,
Huh.
but perhaps even more intriguing, though, is what is the physical chemistry inside the planet? What does this mean for water world? So I can give you an example. Here, the hydrogen has been added to the silicate and the iron. It has not been added as water.
Okay.
It's been added as hydrogen.
Uh-huh.
And we can call it water because if you trace in the ab initio calculations where the hydrogen is living in the melt, it
Yes.
spends some time bonded to oxygen. So if you want to call that hydroxyl or OH or water,
Huh?
you could, even if you were, in fact, if you were to take a infrared spectrum or of that melt somehow, you would see an OH bond length in it.
Okay. Okay.
But it was not added as water. It did not accrete as water ices,
Mm-hmm.
just hydrogen
In situ. In situ.
in situ. So we had argued earlier in earlier papers that you can make water this way, and you certainly can.
Mm-hmm.
So now it becomes a little bit of semantics, right? Is the planet on the right, if you were to strip its hydrogen atmosphere
Okay.
and allow it to outgas, it would probably outgas as water
Yes.
partly. And you would say, well, is that a water world? And maybe it is, but it's an endogenous water world. It's a water world where it made its own water
Mm-hmm.
by the
Mm-hmm.
interaction between the hot magma and the hydrogen.
Mm-hmm. Cool.
So
Very
this is becoming a thing, I think, about trying to understand what it means to have water, to make water, to accrete water, and so forth.
right.
Um, that's really the gist of the paper is that we don't think sub-Neptune. Now we're carrying this further now. When we try to do population studies using this model, what we learn is that something like 20% of all of the planets that lie in what you might call a super Earth plus sub-Neptune field,
Okay.
something like 20% would have metal cores of the
Okay.
type that we think of like Earth.
Uh-huh.
So that's why we say that it's the exception,
The
not the
exception, not the rule.
right.
Very cool.
So that's pretty much the story.
Beautiful. Beautiful work. Beautiful. And there's a couple of very awesome appendices. If you like equations, you should check them out, people. It's pretty good. Pretty good.
Yeah, there's a lot of interesting, like if you want to just have one little footnote, how to deal with adding hydrogen and iron to the melt is really interesting. We are guided by the ab initio calculations,
Hmm.
but then we need to capture those ab initio calculations into something that's portable to a planet model.
Yes.
And that's partly what the appendix talks about. So,
Hmm. Which is a neat trick in and of itself. So do check that out.
mhm.
Very cool. Ed, I want to thank you so much for walking us through your very awesome article. Thank you so much.
Yeah, thank you.
Good story. Oh, let's see. You hinted at it a couple of places or intoned it a couple of places. And so let me ask it this way. Where do you think we can go from here given the published article? Is there additional laboratory astrophysics that could be done to sharpen up some of those unknown constants or to make them more precise? Is there additional observations that might be useful to determine where we are in these diagrams and so forth? So next steps, where do you think we go from
There
here?
are several parallel threads. One is more ab initio calculations, more calculations to understand the phase equilibria in more complex systems moving forward. That's, I think, a generational task. It's going to take a long time because these
They're,
simulations take a very long
they
time.
are not cheap. Yes.
They're not cheap, right? Exactly. Both computationally and human time.
Yeah.
Um, at the same time, we turn to the ab initio calculations because the experiments are limited. We can't get to the conditions that apply deep into a sub-Neptune generally. But
Okay.
experiments are being done, including out of ASU and out of Carnegie. There were two papers in Nature that just appeared that showed that yes, this idea that you make water by reacting silicate melt with and iron with hydrogen that's been demonstrated in the laboratory at pretty high temperature and pressure. So
Good.
we're getting there with the experiments. They're challenging. They're usually done in diamond cells and tiny little samples and hard to
Yes,
measure.
diamond handles.
Right. So that work is progressing.
Cool.
And from the observational side, for a while now, we've all been trying to see whether or not when we get a spectrum, if we get a JWST spectrum, and we see some molecules in the atmosphere, can we say, oh, there is a magma ocean down there or there isn't?
Hmm.
And that is really a challenge. I mean, that is the goal. That's the holy grail. But we need better and better models before we can really say definitively, oh, the absence of nitrogen, for example, means there was a magma ocean. We don't really know that
Know
yet.
that
That's
yet.
where we're headed. Yeah.
Very nice. Very
So,
cool. Well, it's going to be really exciting to see this develop over the next couple of years or generation, as it may be,
yeah.
as we start figuring out the thermodynamics and the interiors of these sub-Neptunes we were discovering. So very nice.
Yeah.
Very
Fun.
cool.
It's a fun time.
Yeah, it is.
Yeah.
Ed, thank you so much for walking us through your very awesome article.
Sure. Thank you. Been
Sure. And
fun.
that'll do, everyone. And I hope this made your astronomy day and your planetary science day just a little bit better. And we will see you on the next one. Bye bye.